Okay. Thank you very much, and I apologize for the problems. I thank all organizers for their kind invitation. It is really a great honor for me to present the result of my research within a so qualified context. I also take the opportunity to present my best wishes to Luca on his important birthday with my congratulations for his continuing contributions to the development of knot theory. Well, my talk will illustrate the content of some joint work with Paola Cristofori, which is my colleague at the University of Modena and Reggio Emilia in Italy. As the title says, they concern the relationships among three different well-established tools to represent PL manifolds in dimension 4. It has the classical one via frame links and Kirby diagrams, the more recent one via trisections, originally introduced by Gay and Kirby in 2016, and as a connection, the combinatorial one via edge color graphs encoding color triangulations, usually called GEMs. This is the plan of my talk. After recalling some basic notions of gem theory, I'll briefly present the algorithmic construction to pass from a Kirby diagram to a gem of the represented 4 manifold, with its consequences regarding the estimation of related invariants and the possibility of obtaining examples of triangulations of exotic 4 manifolds. Then I will introduce trisections induced by GEMs, both directly and through 2 indirect approaches, which allow suitable estimations of the trisection genus. Further, I will focalize on the double passage from Kirby diagrams to trisections via GEMs, which enables to estimate the trisection genus of all closed orientable 4 manifolds in terms of the combinatorial properties of an associated Kirby diagrams. And finally, if time permits, I will show how trisection diagrams can be easily obtained from GEMs, in particular when they arise from frame links. Well, let us start with a brief reminder of the fundamentals of gem theory. As I have already hinted to, it makes use of suitable edge color graphs in order to represent the whole class of PL manifolds without restrictions about dimension, boundary property, and orientability. The theory is also known as crystallization theory, from the name of a special class of representing objects called crystallizations. As it is quite evident, the possibility of performing a purely combinatorial approach to general PL manifolds is of particular interest in dimension greater or equal to 4, where the difference between top and PL categories must be taken into account. An n+1 color graph is a regular multigraph of degree n+1 endowed with an edge coloration. It has a coloration of its edges by means of n+1 colors, so that adjacent edges have different colors. The color set is usually chosen to be 0, 1, n, and it is denoted by delta n. Each n+1 color graph is used to represent the associated pseudo-complex K-gamma, which is obtained by means of the construction shown in this picture for the 3-dimensional case. Each vertex of the graph represents an n-simplex with its vertices labeled by 0, 1, n, while each C-colored edge corresponds to the identification of the n-1 faces opposite to C-labeled vertices. Note that the graph is exactly the one skeleton of the dual complex, the dual cellular complex of the pseudocomplex K-gamma. The space, the associated space in general is an n pseudo-manifold, which is orientable if and only if the graph is bipartite. And the graph is set to represent it. Moreover, it is not difficult to prove that the associated space turns out to be a closed PL manifold if and only if, for every color C, each connected component of the graph obtained by deleting all C-colored edges, which is indicated in this way, represents the n-1 sphere. On the other hand, if all these connected components represent closed n-1 manifolds, then the edge color graph is said to represent a compact PLN manifold, whose possible boundary components are represented by the subgraphs with n colors, not representing the n-1 sphere. In both cases, the color graph is said to be a gem, where gem means graph encoding manifold. Some examples may be useful. This is the standard graph representing the free sphere, two tetrahedra with all triangular faces identified. Again, in dimension 3, the orientable sphere bundle over S1, and the real projective space, that is the length space L21. In dimension 4, the complex projective plane, and the 4-dimensional underbody of genus 1. This is the existent theorem, which gives foundation to the theory, ensuring that any compact PLN manifold admits a regular n+1 color graph representing it. Admits a gem. As a consequence, we can introduce in any dimension suitable graph-defined invariants. A very natural one is the so-called gem complexity of a compact form and manifold that involves the minimum number of vertices in an n+1 color graph representing the manifold. Note that the term complexity is appropriate since by duality, this invariant involves the minimum number of n-simplices necessary to get a color triangulation of the manifold. And in this sense, it is similar to the well-known Matveev complexity in dimension 3. Moreover, gem complexity enables interesting classification results related to automatically generated catalogs, especially in dimension 3 and 4. Actually, the most studied of the invariants arising from gems is the regular genus. It is strictly related to a particular type of embedding of graphs into surfaces, so that the regions of the embedding are disks bounded by bicolor cycles consisting of colors consecutive in a chosen permutation of the color set. Here is an example of a regular embedding of a 4-color graph representing the Poincare homology sphere into the closed orientable surface of genus 2 with respect to the cyclic permutation green, red, blue, and gray. Note that the regions of the embedding are bounded by cycles alternatively colored by green, red, and red, blue in the front side of the surface, so to say, and by blue, gray, and gray, green in the back side. Well, a classical theorem by Gagliardi ensures the existence of such an embedding for any color graph and for any cyclic permutation of the color set up to inverse. Moreover, the surface is orientable if and only if the graph is bipartite. And since an embedding defines a cellular decomposition of the surface, we can easily compute its Euler characteristic and hence its genus by means of a combinatorial formula, where this symbol denotes the number of cycles colored by consecutive colors of, in position I and I+1, while P is half the order of the graph. Well, by taking the minimum genus over all cyclic permutation of the color set, we obtain the regular genus of the graph, while the regular genus of a manifold is obtained by taking the minimum over all graph representing the manifold. Hence, the regular genus of a PL manifold is nothing but the minimum genus of a surface in which a gem of it regularly embeds. The regular genus is a PL manifold invariant which extends to arbitrary dimension the classical genus of a surface and the agar genus of a free manifold. And many classification results have been obtained via regular genus, especially in dimension 4 and 5. Now, let us get into the specific of our theme, illustrating the connections between Kirby diagrams and edge color graphs. As it is well known, Kirby diagrams are a commonly used representation tool for closed PL manifolds in dimension 4, encoding their handle decomposition. According to Argbulut's notation, one handles are depicted via trivial dotted components, while framed components describe the attachment of two handles. Actually, the Kirby diagram represents only the compact form manifold obtained by considering only handles up to index 2, but its boundary is exactly the free manifold obtained by dense surgery on the associated frame link, which is obtained from the Kirby diagram by replacing each dotted component with a 0 framed one, a trivial 0 framed. However, if the boundary is homeomorphic to a connected sum of sphere bundles over S1, then a famous theorem by Lodenbach and Penaru ensures that there is a unique way to attach 3 handles and 1 4-handle, so to obtain a closed manifold. And as a consequence, that closed manifold turns out to be uniquely determined by the Kirby diagram. Well, the construction I'm going to show makes use of connected Kirby diagrams such that their dotted components, if any, must be in good position. This means that besides being unknotted and unlinked them, they are standardly embedded in the plane so that overcrossings and undercrossings never alternate on each dotted component, as you can see in this picture. Obviously, by suitably arranging handles and possibly using Reidemeister moves, we can always assume that a compact orientable PL4 manifold is represented by a Kirby diagram satisfying these conditions. The algorithm starts as step 0 with the construction of a 4-color graph representing the boundary of the compact 4 manifold by using the associated frame link. I'm happy to point out that this starting part of the algorithm has been originally obtained by simplifying a similar one due to Kaufman and Linz, and hence it is appropriate to recall it during this Congress. First, after replacing the dotted components by 0 framed ones, we possibly add a suitable number of positive or negative curves in order to make the width of each non-dotted component equal to its framing. For example, in this picture, this framed component would require 2 additional negative curves since its rise is 2 while its framing is 0. As you can see, the graph is directly drawn over the diagram of the link by taking this subgraph for each crossing, while each curl corresponds to one of these subgraphs, according to the curl being positive or negative. It is worthwhile to note that up to possible addition of a pair of opposite curves, on each frame component, it is always possible to find a particular subgraph called quadricolor, consisting of 4 vertices cyclically connected by edges of all 4 colors, so that each vertex does not belong to the bicolor cycle containing the other 3 vertices. A basic move of our algorithm is exactly related to quadricolors, and it consists in the addition of 3 edges of color 4, color red in the picture, in this way. When dotted components are missing, this is all we have to know, because once the 4-color graph the 4-color graph of step 0 has been drawn, the edges of the additional color 4, or red in the picture, are added by doubling the 1-colored ones everywhere except for the triad of 4-colored edges concerning the vertices involved in the vertices of the quadricolor for each frame component, in the way we have already seen. The case when dotted components appear is more complicated, and the algorithm depends on some choices of points and arcs and parts of arcs of the diagram. Here are the choices we have to make. On each dotted component, we have to mark 2 points, H and H prime, such that they divide the dotted component in 2 parts, one containing only overcrossing and the other containing only undercrossing. Then we have to cut each frame component in a point X, where quadricolors will be positioned. Another choice, we have to highlight a sequence of consecutive arcs on each framed component, starting from the cut X, so that the 2 vertices, the 2 points, the 2 chosen points, H and H prime, belong to the boundary of the same region of the plane when the cuts X and the highlighted arcs are removed. For example, in this picture, the gray regions will merge into a unique region if we delete both the cuts, the red cuts X, and the yellow arcs. And so H and H prime belong to the same region of the plane. Well, to construct the 5-color gem, we have to add the 4 colored edges to the 4-color graph obtained in step 0. Let us see the main steps of the construction. After locating the quadricolors on each frame component, on each part of the graph corresponding to a frame component, the highlighted arcs identify parts of the graph where to add 4 colored edges transversal to the arcs themselves, transversal, so to say. Then the points H and H prime prime identify a pair of vertices V and V prime on each dotted component, which have to be connected by a four-colored edge. Then on each quadricolor, we add a triad of four-colored edges according to the described move. And finally, the remaining four-colored edges are added so to close paths of colors 1 and 4. This is the output of the algorithm for our example, and we have proved that the resulting graph is always a gem of the compact manifold represented by the starting good Kirby diagram. The essential point of the proof is that this five-color graph can be constructed from the four-colored one by sequences of combinatorial moves with a precise topological meaning. I'll only give a little hint. First, if we perform on all quadricolors of the graph obtained in step 0 the change of one colored edge shown in the picture in green, we obtain a graph representing a connected sum of sphere bundles over S1, where the number of copies is equal to the number of dotted components. Then, by doubling the edges of color 1 with 4 colored edges, we obtain a 5-color graph which represents the product of this connected sum of sphere bundles over S1 with the unity interval. And then the graph, the switching of 4 colored edges involving vertices V and V prime for each dotted component translate attaching one handles on one boundary component of this product for the unity interval, while the attachment of 2 handles on the other boundary component are translated by the moves on quadricolors. And so the obtained four manifold has the handle decomposition encoded by the Kirby diagram. Now let us see some applications of the construction. The first one regards the possibility of estimating both the invariance regular genus and the gem complexity of the represented four manifold by means of combinatorial properties of the Kirby diagram. In fact, it involves the number of crossing, the number of framed and dotted components, together with other elements that can be easily computed by the diagram. Moreover, only in the case of frame links, that is, when dotted components are missing, or equivalently when the handle decomposition lacks in one handles, it is possible to yield a significantly better upper bound for regular genus, which turns out to be sharp for infinite families of four manifolds. In fact, in this case, the 5-color graph obtained by the described algorithm may be transformed via the so-called generalized dipole moves, which are graph moves not affecting the represented manifold, into another 5-color graph with regular genus M alpha plus L, where L is the number of components of the diagram, while M alpha is the number of alpha color regions in a chessboard coloration of the diagram, alpha being the color of the unbounded region. A further result regarding invariance, which directly follows from the described construction, concerns the regular genus of the subgraph without color 4, which represents, as we have already pointed out, the free manifold obtained by dense surgery on the associated frame link. In the general case, that subgraph has regular genus equal to the crossing number plus 1. Moreover, if dotted components are missing and the simplified gem is considered, its regular genus is exactly equal to M alpha, the number of alpha color region. And this result will be of particular interest when we deal with trisections. This is an example. For example, if we consider the trefoil knot with framing 1, this is the 4-color graph representing the associated free manifold, while this is the 5-color graph representing the 4 manifold. Since no one handle appears, no dotted components, we can calculate the number M alpha. 2 is the number of alpha component, alpha regions colored by alpha in a chessboard coloration of the trefoil knot, and hence, according to the statement, the 4-color graph may be transformed into this 4-color graph whose regular genus is 2, and the 4-color graph can be completed with color 4 in this way, and this is a gem of the associated 4 manifold with a regular genus free M alpha plus 1. Another consequence of the described construction regards the possibility of obtaining examples of triangulation of exotic 4 manifolds. For example, Paola Cristofori and I have applied the construction to this pair of exotic 4 manifolds represented by Naoe in a paper published in 2019 on in experimental mathematics. These are the 5-color graphs representing a triangulation, scalar triangulation of this exotic pair. Obviously, exotic pair means that they are 4 manifolds which are PL homeomorphic, but not top homeomorphic, but not PL homeomorphic. Well, other examples of triangulation of exotic pairs may be found in a recent paper by Riley Burke, where also the first triangulation of quarks appear. In fact, he implemented our algorithm in a software utility of Regina software package by Ben Barton and his collaborators, which gives the additional advantage of allowing the manipulation of the resulting triangulations through an expressively thought of heuristic for the 3-dimensional case. Well, let us now introduce the third representing tool we are dealing with by recalling the notion of trisection. It was introduced by Gay and Kirby in 2016, in some sense extending the 3-dimensional idea of Egar splitting. As everyone knows, each closed free manifold may be split into 2 3-dimensional endel bodies intersecting in a closed surface, and the related invariant, the Egar genus, is the minimum genus of a splitting surface for the free manifold. In dimension 4, each smooth closed 4 manifold may be decomposed into 3 four-dimensional handle bodies, mutually intersecting in three-dimensional handle bodies, so that the intersection of all three pieces is a closed connected surface, which is called the central surface of the trisection. This cartoon gives an idea of the splitting translated into a two-dimensional setting. The minimum genus of the central surface is said to be the trisection genus of the closed form manifold. In the last years, the notion of trisection has been extensively studied also in its relationships with other manifold representation tools. In particular, in 2018, relying on the difference and on the coincidence between different PL categories in dimension 4, Bell, Haas, Rubinstein, and Tillman faced the study of trisections via color triangulations, thus turning trisection from smooth to PL category. Our approach to trisections moves from the intent to generalize both the idea of Bell, Haas, Rubinstein, and Tillman and the smart one by Spreer and Tillman, who were the first to establish a connection with gems by making use of a very special class of crystallizations. Well, excuse me again, there is a problem with the slides. Excuse me. Why? It is not a good day today. Perhaps I have. Okay, I am here. Do you see the slides?
Yes. Yes.
So, excuse me. Well, Paola Cristofori and I proved that each gem of a compact PL manifold with empty or connected boundary, both in the orientable and non-orientable case, induces a decomposition of the manifold which resembles a trisection. There are three four-dimensional pieces, two of which are handle bodies, while the third one is a color on the boundary or a four disc if the boundary is empty. All three pieces intersect in a closed surface, but only two of the pairwise intersections are ensured to be handle bodies. Obviously, we are interested in the case in which also the third three-dimensional intersection is an handle body. If this happens, the decomposition is said to be a gem-induced trisection, since it is an effective generalization to the connected boundary case of the notion of trisection. Okay. The window is not adapted, perhaps. Well, It generalizes the notion of trisection to the connected boundary case, while in the closed case, it is exactly a trisection of a special type, that is the type in which one of the four-dimensional body is a disk, is a four-disk. This zero means this fact. What is interesting with the gem-induced trisection is that the genus of the central surface exactly equals the regular genus of the subgraph without color 4. We have detected the condition, the combinatorial condition, which ensures the collapse of the third three-dimensional intersection, so to have a gem-induced trisection. Without going into details, what is required is the possibility of ordering all 4 color edges of the 5-color graph, so to satisfy a suitable property involving bicolored cycles, which exactly corresponds to a collapsing sequence of the third three-dimensional intersection. What is important to point out is that the gem-induced trisections fit Gay and Kirby's definition of trisection, hence allowing a direct estimation of the trisection genus only for a suitable class of closed orientable four manifolds, characterized by admitting a handle decomposition with no prehandles. What is good is that this class possibly comprehends all simply connected four manifolds, according to a famous open problem by Kirby. But certainly one can't face the whole class of closed four manifolds directly by gem-induced dissections. Nevertheless, there are 2 indirect approaches to trisections of closed four manifolds, starting from gem-induced trisection. The first indirect approach relies on the particular type of extension to the boundary case performed by gem-induced trisections, where one of the four-dimensional piece is a color on the boundary. In fact, if this boundary is a connected samosphere bundle over S1, it is not difficult to prove that any gem-induced trisection naturally gives rise to a trisection of the associated closed four manifold, that is the closed four manifold obtained by gluing a four-dimensional underbody along the boundary, which is uniquely determined in virtue of the Lodenbach-Penaru result we have already quoted. And as a consequence, since the central surface is not affected, an upper bound for the trisection genus is obtained, and in particular, this upper bound turns out to be sharp for a wide class of orientable and non-orientable four manifolds, comprehending all standard simply connected four manifold, but also non-simply connected ones. The second indirect approach is used when the third in three-dimensional intersection does not collapse to a graph. In this case, we exploit the possibility of performing a so-called stabilization of the splitting. Roughly speaking, each stabilization consists of adding a one handle to one of the four-dimensional pieces, in our case, the one equal to the four sphere or to a color on the boundary, without affecting the other 2 pieces. At every step, the genus of the central surface increases by 1. But the collapse of the third three-dimensional intersection is ensured after a number of steps which is at most equal to the difference between the regular genus of the graph and the regular genus of the graph without color 4. And by combining this second indirect approach to the first one, we obtain we proved that a trisection arises from each gem of a compact four manifold, both in the closed case, when M is equal to 0, and in the case of the boundary equal to a connected sum of sphere bundles over S1. And the genus of the obtained trisection turns out to be less or equal to the regular genus of the starting gem. In particular, when the manifold is closed, the regular genus turns out to be an upper bound for the trisection genus. And hence, the strong relationship between trisection theory and gem theory turns out to be certified also by this relation between the involved invariants. Well, if it is possible, I would like to explain you that till now we have seen how to pass from Kirby diagrams to gems through an algorithmic procedure, and then how trisection can arise from gems, either directly or indirectly. And hence it is natural to investigate the double passage from Kirby diagrams to trisections via gems to search if it is possible to combine the obtained results. Well, rather surprisingly, for each Kirby diagram in good position, the 5-color graph obtained through our algorithmic procedure always admit a gem-induced trisection. By construction, its combinatorial properties ensure the possibility of ordering its 4-colored edges so to satisfy the above-described collapsing condition. And moreover, if the Kirby diagram represents a closed four manifold, that 5-color graph is a gem of the compact four manifold consisting only of the union of handles up to index 2, whose boundary is exactly a connected sum of sphere bundles over S2, as required by the first indirect approach. And we know both its regular genus and the regular genus of its subgraph without color 4. As a consequence, an estimation of the trisection genus of each closed orientable four manifold is obtained. It involves the crossing number of the Kirby diagram in the general case, while it depends only on the number of alpha-color regions in a chessboard correlation of the diagram if no dotted component appears. I don't know if I can give a hint about the trisection diagrams or if my problems have caused the lack of time. I can do as you want.
I mean, if you want a few more minutes, you started late, so you can have a few more minutes if you'd like.
Okay, yes, I can. I only add that there is a further element that strengthens the relationships among the representing tools we have considered. It concerns the possibility of obtaining trisection diagrams directly from gems. According to trisection theory, a trisection diagram consists of 3 systems of curves lying on the center surface that allow to reconstruct the whole decomposition, since they constitute in pair Egger splittings of the boundaries of the 4-dimensional pieces of the trisection. Well, without going into details, I can say that if a 5-color graph gives rise to a gem-induced trisection, then a trisection diagram may be obtained simply by considering suitable subsets of bicolor cycles of the graph, which may be combinatorially identified by following the collapsing sequence of the third 3-dimensional intersection. For example, this is a gem of the product the S2 cross S2, which admits the depicted ordering of 4-colored edges, realizing the collapsing sequence via suitable bicolor cycles. As a consequence, this trisection diagram can be obtained with the 3 systems of curves on the central surface, which is genus 2, which in pair gives rise to agar diagrams of the boundaries of the 4-dimensional pieces. And in particular, if we start from a framed link and if we consider the gem algorithmically drawn directly on the link itself according to our simplified algorithm, then the 3 systems of curves are given by bicolor cycles of these pairs of colors. And what is interesting is that this last result holds also in case the framed link represents a 4-manifold with boundary, thanks to a suitable extension of the notion of trisection diagram to simply connected 4 manifolds with connected boundary. This is the example we have already seen, the gem representing the 4-manifold obtained from the trefoil with framing 1, and this is the obtained trisection diagram on a surface with genus 2. It is not always so simple to obtain trisection diagrams from gems, but it is always possible and can also be performed automatically by a suitable computer program. Thank you for your attention, and I apologize for multiple problems.
Thank you very much. Thank you. Let me turn off recording.